Live stream. Streaming within redirecting to YouTube.
స్టాప్ చేయాలి
వద్దు వద్దు అది ఆటోమేటిక్ ఇది అన్మ్యూట్ హలో
Kavin.
So good morning, ma'am. Good morning, Dhanalakshmi ma'am. Good morning, all.
Good morning, sir.
Yeah, good morning, ma'am. Good morning.
Recording doesn't yes, ma'am.
Good morning, ma'am.
Good morning.
Good, sir.
Good morning, ma'am.
Good morning, participants.
Video on this.
Good morning, participants. Our resource person, Dr. T. Senthil Kumar, sir, Associate Professor, Department of CSC, Amrita School of Engineering, CBE, India. Today's demo on usage of deep learning algorithms and malware analysis. Sir, you can continue. Sir. Dr. P. Senthil Kumar, sir, Associate Professor, Amrita School of Engineering, CBE, India. Sir, sentence, sir.
Ma'am, shall we start?
Yes, sir.
Okay, right, fine. Okay. I think you have to give me host enabling, ma'am.
Okay, sir.
Okay, sir.
Fine. Okay, ma'am.
Make post. Yes, yes.
Well, share the screen.
You can start.
I think now you're able to see the screen, ma'am.
Yes, sir.
Fine. Okay, ma'am.
Tension would be.
So good morning to you all. Thanks again for joining the session. So today we will get through with the hands-on learning of how to take data set and how to analyze the data set using machine learning algorithms and deep learning algorithms. We'll also show you some outputs that will give you some insights about how to take your real-time data, whichever you want to analyze, and see how it can be.
Sir, your screen.
Today we will get through with the hands-on.
Screen study.
Yes,
Screen.
Okay. So yesterday's session we had given a quick summary of what is deep learning, why deep learning is important for data set analysis. Then we started our discussion about the deep learning architecture, CNN, that's convolutional neural network. In summary, few things that we had kept for learning for all of you is one, we had said that deep learning has got layers, but that's called as hidden layers. But again, the hidden layers have special names like convolution layer, pruning layer. And this layer concept differs from one architecture to another architecture. Okay. The next one that we have kept for your references, there is something called as hyperparameters that you have to set for every model. And these hyperparameters are very crucial because they allow you to learn the given data and give you output. So the output is measured in terms of the performance metrics. So there we had said there are performance metrics like precision, recall, accuracy, F1 score. Then we had said about sensitivity also. Now, the next thought process we would quickly take into is the variant architectures which are there in deep learning. Then we'll come down to the code and followed by demo. See, we said convolutional neural network as such has data as input and it can give you an output. Now, our next discussion forward is architectures which can remember the past data. See, CNN differs from other architecture because CNN cannot associate the current data with the past data. To give you more clarity, let's take you have been given with 10 textbooks to learn and you are given an 11th textbook to learn again. You would say that I learned 10 textbooks. The 11th textbook I am able to learn by relating to what I learned from the 10th textbooks. That's the last 10 textbooks. So the concept of remembering is not generally there in terms of CNN, but RNN gives you the capability to say that you can actually remember the data and associate the data with what you want to compare under the test process, and you can give quick performance in terms of accuracy, precision, recall, F1 score, right? Now let's come to the architecture RNN. RNN stands for recurrent neural network. As I told you, it will store the state of the previous input and combine with the current input, and it will be able to preserve some relationship of the current input with the previous input. So this is a very interesting thing of RNN. So you give n types of data all n types of data it will be able to learn and give you a quick relationship and say it belongs to a specific class. Now the formula for the state would be spoken in terms of two things. One is a current state and next is a previous state. What you see in the diagram here is an working of an RNN. Here you can see there is something called as X, which is the input which you want to provide, and you see something called as Y, which is the output that you get. So given some input called as X, using an RNN, you would like to generate an output which is called as Y. So every time you would like to calculate the state. So let's see the state equation here. So the formula for the current state is given as H suffix t is equal to f of H suffix t minus 1 comma x comma t. So what is H suffix t minus 1 is nothing but the previous state, and the current state you get every time is called as H suffix t. And x suffix t is nothing but the current input you give to the model, right? So every time you are trying to compare with the previous state is nothing but H suffix t minus 1 to understand the current state. So the learning of the model is dependent on state here, and the state varies from over the time for every input that you provide. The activation function for CNN is generally called as ReLU, right? But when you come to the RNN, the activation function will be tan H. So you write it as H suffix t is equal to tan H of W suffix HH into H suffix t minus 1 plus W suffix XH into X suffix t. Now let's see the meaning of each of this. The first parameter that you see here, that is W suffix HH, is nothing but the weight at the recurrent neuron. And W suffix XH is nothing but the weight of the input neuron, right? So every time you can see here, the recurrent neuron as such is taking the previous input state, right, into consideration, and it actually works for longer sequences, right? So longer sequence in the sense, if you talk about a data which has got 5 features, and then you say 10 features, then you say 100 features, so your every row of data is one line sequence. So the size of the sequence is longer. So for longer sequences, RNN is most appropriate, right? So once you calculate the current state, that is H suffix t, you will be able to get the final output. The final output is called as Y suffix t. So you say Y suffix t is equal to W suffix hy into H suffix t. So H suffix t is nothing but the new state. Y suffix t is nothing but the final output that you get every time, right? So RNN is generally used for NLP, natural language processing, but you can very well use RNN for intrusion detection classification also. I'll show you the online source also for it. Now when you come to RNN, there are different variants of RNN. First is called as one-to-one. That means you give one input, you get one output. Next is one-to-many. You give one input, you get many outputs. So as you can see here, the state output of one recurrent neuron becomes an input for the second recurrent neuron. The state output of the second recurrent neuron becomes an input for the third. Third becomes an input for fourth. This goes to for all the sequences. Next is many to one. As the keyword indicates, you give many input, but you get only one output here. The last one is called as many to many. In many to many, you see two architecture models here. In the first case, what do we say is the number of inputs is equal to number of outputs. I'll repeat again. The number of inputs here is equal to number of outputs, right? That means you say T suffix X is equal to T suffix Y. The second case is the number of inputs will not be equal to the number of outputs. That means the input layers and the output layer size may not be the same. The input layer size and the output layer size may be different, right? Okay. So this is the next one, that is many to many. Now what we have seen is the different variant architectures of RNN. Now let's take a sequence to understand how RNN works. Now if you can see here, there's a letter called as hello, H-E-L-L here. So next occurrence character is going to be O, right? Every input that you take in a packet sniffer is going to be a sequence. Please always understand, every input that you take in a packet sniffer is going to be a sequence. So here you have a binary sequence here, representation for all of this. And this is the next one that you should understand here. Any data that you provide, right, the data as such need to have a binary representation for it. So how do you get your binary representation? That's the next question somebody would ask. So you can actually get your binary representation by using a concept called as one-hot encoding, right? One-hot encoding. I'll show you here. You go to the internet and type one-hot encoding. You have the code library also in Python, right? One-hot encoding. You can see here. One-hot encoder, right? It's under the sklearn library in Python. So the purpose of one-hot encoding is any data that you provide, if it is not a binary sequence, if it's a categorical value, then you can convert from categorical value to a binary sequence using one-hot encoding, right? Now, let's move on to the presentation. Now, the input sequence is HELLO. So you take HELL. For each of it, you give a binary representation, right? Each of it, you give binary representation. Now, the requirement of an RNN here is, if I give a character sequence like this, saying H, E, L, L, it should be able to say that the next character that is going to come in is going to be O, right? This is very interesting to understand because when you take any real-time data, especially the network flow traffic that you take, as the data is coming in, you'll be interested to see what is the next packet data that you'll be getting. The next packet data will be O or next packet data will be G, but your model should be able to say that no, the next packet data that you'll be getting is only O here. So let's see how it does. Now the theory remains the same. Theory remains the same in the sense, if you can go to the fundamentals where we started, we said we have every time we need to calculate H suffix T, right, which is dependent on W suffix HH, which is the weight at the recurrent neuron. And next is W suffix XH, which is nothing but the weight of the input neuron, right? And whatever you get from H suffix T will allow you to calculate the final output, which is Y suffix T. So Y suffix T will be given as W suffix HY into H suffix T. Now let's see the step 1 here. You have H here as a first part. Take H. Okay. We got W suffix XH. Take W suffix XH. Now multiply W suffix XH into H value. Now when you multiply, you will get an value which is equivalent to what you see on the right side, which is the product of W suffix XH multiplied by the binary representation for H. Okay. Now, the next step that we would go into is, we have to go into the recurrent neuron and assume what is the weight of the recurrent neuron. Because every time we need a weight, right, for the recurrent neuron that you take. So the recurrent neuron is supposed to have a weight, which is called as W suffix HH. So we want to take a weight for the recurrent neuron. So the weight for the recurrent neuron, we are taking here as 0.427043, right? And the bias is also required, right? Because we told already yesterday saying that it is WX plus B always. So you need a bias. So the bias in this case, we are assuming it to be 0.56700. Now, the concept of recurrent neuron says that anytime you get an input character, you are associating your learning from the previous. So now how H is the input character that is being provided, you would like to associate it with the previous character. But there's no previous character with which you have learned, right? Because this becomes the first character here. So when H is being provided, since there is no previous state here, we will take the same equation and substitute, right? So what is the equation says? W suffix HH. What is W suffix HH? Is the weight, which is 0.427043. Participants, please all of you listen. This will be slightly hard to listen, but sometimes it's very easy to accept at the end because you can use it for a lot of projects and research. Next is H suffix T. So the H suffix T is 0.56700, right? So here, this 0.56700 becomes your bias, Now, the next that we multiply is the sequence of previous character. As I told you here, the input character is H, but we don't have any previous character at all, right? So naturally it becomes 0. So 0, 0, 0. Now you multiply, you take this W suffix HH, right? And then you take bias, apply it in the equation here. You are supposed to get value as 0.567001, right? So now the next step forward would be is to apply on this equation, because we have got two values, right? The first set of values that we have got is with respect to the given input character, which is 0.287027, 0.902874, 0.5375624. This is the first that we got. Now you take that value and substitute it on the first part. The second is what? What is the value that you got for the, assuming the previous one, that is previous character of H is 0. Assuming that, we got it as 0.567001. So take that and place it here. The equation says what? You have to add this together, add these two values together, right? So I think people know very easily, right? It is 0.56, 0.28, you add together, it is 0.85, right? Like that, you add the next two values, 0.90 and 0.56, 0.53 and 0.56, you get this values. Now on this value, you are supposed to apply a tan H function. So tan H of this values, you get H suffix T. Now step 3 is over. Now let's come to step 4. What does step 4 says? It says that now let's go on to the next state. We have learned H, right? We have learned H, assuming that there is no previous character with respect to H, right? Now the next character in sequence is E. Now given E, how do you apply, right? So the equation that we got earlier is what? H suffix T, right, is equal to tan H of, right, the values that we got. So what is the value that we have got here? In this case, the value that we have got here is 0.69, 0.89, 0.80. This is the first part. You can see here, right? Now, let's go to the character E. Now, with respect to character E, we have to take the same equation, that is tan H of W suffix HH, H suffix T minus 1 plus WXH, X suffix T, right? Now, this can be written in general with respect to the bias. How do you write it with bias? This is the equation here, W suffix HH into H suffix T minus 1 plus bias is equal to the original value that we have got, that is 0.427043. So what is this 0.427043 is this one. You can see here, the weight of the recurrent neuron is 0.427043. So take that and put it here, 0.427043, right? Multiplied by H suffix T minus 1. So H suffix T minus 1 that we got is what? 0.693, 0.899, 0.802. Now take the values and put it. Plus bias. So the bias value that we have assumed is 0.56700. Now take that value and place it. 0.56701. Now when you multiply this two part and add it with this one, the resultant value you will be getting is 0.86, 0.95, 0.90. Right? So this is your WXH, right? This is your WXH. Now, if you see this WXH that you have populated here, this is your WXH with which we started. You can see here, right? Wait for H, E, L, L, right? Now, the next step would be WXH, right? Multiplied by the given character sequence, that is E. The resultant is, you will get a value like this, 0.84, 0.87, 0.09. Now we have done for two characters, H and E. Now what we do is, we want to find what would be the next state, assuming E here. So H suffix T would be given as tan H of the first set of values that we got is 0.86. You can see here. Okay. Yes. 0.863013, 0.951149, 0.90954. That is WHH into H sub x t minus 1 plus bias. Take the values and put it. Plus double XH into X sub x t. 0.84, 0.87, 0.09. We're just substituting in this equation, that's all. Now you get a resultant value like this: 0.93, 0.94, 0.76. Okay. Then this is you're getting after adding this two and then doing a tangent, right? So the next step that we are supposed to do is what? Substitute it to get the value for y suffix t. So y suffix t would be w suffix hy into h suffix t. So w suffix hy that we have got earlier can be taken, okay, into h suffix t can be substituted. The resultant one you get is y suffix t. Right? Now this becomes the class-wise probabilities for the next letter. Right? So softmax of this value will give you values as 0.41, 0.194, 0.16, 0.22. So here we have taken for two character sequence, H and E, right? Now similarly, the next sequence also will be learned as per this model. So every character sequence will be automatically classified with a probability value that you can see under here. So this is how RNN works. Now in this part, people usually ask a question: how does RNN does a back propagation? Right? Okay. So as far as the forward propagation is concerned, it is easy to understand because you give a character H, the recurrent neuron learns, gives it to the next, and so on. Right? Okay. Now in case of backward propagation, right, we have to change the weights. So this is generally done based on a loss equation like this, which you can see here. This type of loss that we calculate here is called as cross entropy loss. Right? So what are the general steps that happens for back propagation is this. First, it actually calculates a cross entropy error using this equation. Then it will allow the network to remember that, right? Then for the network, whenever it's going through the back propagation, the gradient will be calculated again, right? And it will combine in the next phase, that's the next pass. And finally, the recurrent neuron will learn for all the neurons in the model. So there's the next one I want to clarify. Any questions from the participants on the stage before we move on to the next concept? Participants, any questions? It's a good silence. Participants, any questions from your side? Am I audible? Hello? Madam, am I audible? Hello?
Yes, you are audible, sir.
Okay, fine. Thank you. Thank you for acknowledging. Okay, so there is no questions from the participants. Now we will move on to the next part of learning. Now we'll spend some time to implement some concepts and see how it works. Okay, so for understanding side, we will do the demonstrations with Google Colab so that you also will be able to configure your Gmail account and parallelly use it with Google Colab. Okay, so that's the plan here. One second. I'll share the screen. Yesterday I told you, if you have any data, so what do you normally do with the data is you go and ask whether there is a class with the data, whether there's a class label to the data. If there's no class label to the data, the solution is you have to run through an unsupervised learning algorithm, right? And you have to associate it to a respective class. Now when we do it, the first question somebody would ask is, my data will not have categorical values, right? Then it is not a problem. But suppose my data has got some categorical value. For example, packet type is a categorical value. It will not be numbers. So there, if you run k-means, it will not work. So you will have to convert your data into a numerical data. Then feed it to the model. Only then your model will work. So how to do it? For that, you can use this method called as one-not encoder. So the purpose of one-not encoder is to convert a categorical data into a numerical data, right? So let's see how we do it. Now, I have already told you that there are data sets on the internet for working, so which we will also take here for analysis. One data set, as I told you, if you have checked in yesterday, you would have got more inputs also. One is Kaggle. If you go to Kaggle intrusion detection data set, you will get data sets, right? So we have said that there's a data set for you to work. Then other one that we have told you is there is a data set called as IoT botnet data set. Okay. It's a data set called as IoT botnet data set. So we are told that these two data sets are very interesting to work. There are so many other data sets, but with my limited knowledge, these are the data sets that I am highlighting to your reference. Now, the next is like, how will the data set look like? That's the first question somebody would ask. See, a data set as such will have features. It will be for more than one columns. You cannot expect your data set to have just one column alone. Your data set will have more than one columns. Now, whatever may be the data set that you have, now our question is, I would like to run a class label generation process. So let's go into how K-means algorithm work. So K-means algorithm, what it will do is, it will take a given data, it will split the data into set of clusters, and the cluster variable can be called as K. So if you say two clusters, it means that it is a two-class problem. If you say three clusters, it's a three-class problem. But ideally, any data can become a n-cluster problem. That means there can be n number of classes. So when you run a K-means clustering algorithm, what happens is every time it will calculate the centroid. So the centroid of the K clusters, right, would become the labels. For example, if you go to a class, right, and there are around 60 students, I ask the students saying, students between 10 to 20, right, roll numbers, sit on one side, 20 to 30, sit on the left side, 31 to 40, sit on the right side, and 41 to 60, sit on the rightmost side. So if I ask you a question, how many clusters are there? You would say 1, 2, 3, 4, because we talked about 4 varying ranges. So every time you are computing a cluster, that is dependent on some condition. I told you roll number. Somebody may say it's a placement performance, right? Students have got marks between 80 to 90, one class, right? 70 to 80 is one class. 60 to 70 is one class. Less than 60 is one class. I got 4 clusters. So the way of clustering is domain centric. Please make a note here. It's domain centric. Based on the problem that you work, your domain will say that this is the way in which you can form a clusters. Now the question here is, I would like to form a clusters. That's all. So when I want to form a clusters in K-means clustering, the first step is called as data assignment step. What do we do in this data assignment step is, if you have a set of data, we would like to find first the centroid. What a centroid is, again, it's a mean on the given data. After I have found the centroid, I would like to take every data and check whether it is closest to the centroid or not. Right? I like to take every data and check whether it is closest to the centroid or not. So this can be done by comparing and checking for the minimum distance. For example, if you are actually saying you belong to one class of cluster, you would actually say, I belong to this cluster because I match. So what is a matching? That can be called as a centroid, right? So you can actually fix some rules and say, whichever centroid value that you got, which cluster it matches. Whichever cluster it matches, you can fix yourself to the particular cluster, right? This is the first step called as data assignment step. Second step is called as centroid update step. What is the centroid update step? Now, I have 5 people in the class who have newly joined. I ask all the 5 people to go and form into some group. They say, sir, I'm into group 1, group 6, group 7, group 8, group 9. We got 5 groups. After 10 days, they again say that, sir, my learning part is becoming less. I would like to move from this group to the other group. So that's a possibility for the centroid also can get updated over the time. When the centroid gets updated, the instances which belongs to the clusters also will get updated, right? So that's the next one here, centroid updation process. We'll see with an example, right? Now, this is the most important thing in k-means clustering called as elbow algorithm. So what is elbow fit algorithm here is? Here, the x-axis you can see the number of clusters. I say number of clusters is 5. So I have 5 clusters. For every cluster, what do we see is, we see what is the average within the cluster distance to the centroid, right? So with respect to cluster 1, cluster 2, cluster 3, cluster 4, cluster 5, you find the lowest one, right, at which the cluster centroid has reduced a lot. There, you can take that and you can fix it as a number of clusters. Reason is, see, if you say I've got 100 instances, somebody says split them into 5 groups, somebody says 6 groups, somebody says 7 groups. So what is the optimal value of the group? Whether it can be 5, 6 or 7, that's the next question. So there, you have to find this elbow point. So the lowest point at which the average within the cluster distance gets reduced, that you can fix it as an elbow point. Otherwise, what happens is the number of clusters that you fix on the given data varies from one person to another person. You will say 5, other person will say 6, and so on. Now let's take an example here. This is for now when we end the code, we will. Now this. Hello. This is your sample data. I have 2 features. Feature 1. I have 2 features. One is 1. So if you put the first feature 1 is 185 and feature 2 is 72. Like this, you can actually have any number of features. Somebody would say, it is not only 2 features. In my data, I have 1 more feature also. In that case, you can assume 1 more features also to the right side. Right? I'm talking from the real-time examples. So here, somebody would say the feature is 23, 45, 33. Okay. I'm just giving some random values. Right? So now if somebody is asking you, what is the size of the feature vector? You should immediately say the size of the feature vector is 3. What is the dimension of the data? Dimension of the data is 2, because every time you look at a dimension, it's across an x and y. So it is n minus 1. So number of features is 3. So it is 3 minus 1 is 2. So the dimension is 2 here. So if there are n features, the dimension is n minus 1 dimensions. Right? Now this is your sample data and this is your feature. This can increase more than 2 also. Right? Now, for our discussion, first step, we are taking 2 features. So with this, let's see how your k-means works. So you need to compute your centroid, right? So we are assuming every data to be classified as a 2-class problem. That means cluster 1, cluster 2. So you call the cluster names as K1 and next you call the cluster name as K2, K1, K2, right? Now when you take the clusters, you have to find the centroid. Centroid means what? You have to find the mean of x. All of us know mean, right? I did not explain. So you find average, right, of x. That becomes the centroid value here for the first cluster and second for the second cluster. Now, this K1, K2 that you take could be random. Somebody would say, I would take this first sample, okay? I would take fourth sample, fine? I would take sixth sample, okay? For all these three, that means 185, 179, 188, I find the mean. Similarly, Y is another feature, right, for the data. So 72 plus 68 plus 77, I find the mean. But that is not a very good process always. So what we do is, we take it in sequential order. So we take first three, find the centroid, right? For the first three, the centroid values with respect to X and Y is 185, 72, right? And similarly with respect to the next three, right? The centroid values that we get here is 170, 56. Okay. Now we need to compute the distance of every instance in comparison to the clusters. So cluster 1 centroid is what? 185, 72. Cluster 2 centroid as such is 170, 56, right? Cluster 2 centroid is 170, 56. Now what we do is, we take every row of data and find the centroid distances. So first one, if you take here, check with this first cluster, it will be 0, correct? So 185, 72, this is again 185, 72, right? Now come to the second one. Second one, you take 170, 56, right? And compare it with 185, 72. Now, if you see the distance, you know the Euclidean distance equation, right? X1 minus X2 the whole square plus Y1 minus Y2 the whole square. So it will be 185, 72 is a centroid, and the data instance is 170, 56. Find the distance. So it will be 185 minus 170 the whole square plus 72 minus 56 the whole square. Take the square root of it will be 21.93. So we take one more just to understand things better. The second data that we get here is 168, 60, and the centroid value is 185, 72. So what will be the equation? 185 minus 168 the whole square plus 72 minus 12 the whole square. Take the square root of it. It will be 20.808. Like this, you will actually find the distance of the centroid to all the other data. That means 179, 68, 182, 72, 188, 77. Now once this is completed, we have to go for the second cluster, right? Because every data we have to check for both the clusters. Now you take the second cluster here. The second cluster centroid is 170, 56. Now go and compare. How will you compare? 185 minus 170 the whole square plus 72 minus 56 the whole square. Take the square root of it. So you get the first value, right? First value is 4.472. Similarly, you compare 170, 56 with all the other instances. You get the values. Now populate the values to the table. Once you populate with the values to the table, for every row of data, you got two cluster distances. One with respect to C1, and another one that we got is with respect to C2. For example, if you take 185, 72, right, you are comparing with cluster C1. What is cluster C1 centroid? 185, 72, right? If you compare with that, it is again going to be 0. Now compare with the cluster 2. Cluster 2 is what? 170, 56. The value that we got is, you can see here, 21.93. Now take 21.93 and place. Right? We'll see one more, then we'll go on to the next. The second data is 170, 56. Right? The second data is 170, 56. Now you are comparing with the first cluster. So the value that you get is 21.43, right? Here. Now you take the value and paste it. Second cluster, centroid is anyway 170, 56, right? You get the distance value as 0. You get the distance value as 0. Now keep it. Now you do for all the data. There are 100 lakh records. For every record you have to do this. Once you are done, then the next step is what? Cluster assignment step. So cluster assignment step, what is the theory that we said? Whichever cluster is giving you the minimal distance, right? Whichever cluster is giving you the minimal distance for the given data, to that cluster the data belongs, right? Whichever cluster is giving you the minimal distance, to that cluster the data will belong. Now look at this data here. For the first row, it belongs to C1 because it is 0. Second row, it belongs to C2. Third row of data, it belongs to C2 because 4.4 is less than 20.8. Fourth cluster, it belongs to C1 because 15 is greater than 7.2. Fifth cluster, 3 is less than 20, so it belongs to C1. Sixth cluster, it belongs to C1 because 5.8 is less than 27.65. Okay, right? Now, the next step is going to be the centroid update step, right? Now we got the centroids, right? And we got the clusters to which each of the data belongs. So what do you say? First row is class 1, second row class 2, third row is class 2, fourth row is class 1, fifth row is class 1, sixth row is class 1. But we still have a doubt whether this data can actually fall into some other cluster if the centroids are updated, right? This is the initial centroid that we assumed, right? So this is the initial centroid we assumed. So how did we assume the initial centroid? We assume the initial centroid by randomly picking the data. So this is centroid 1, this is centroid 2, like that we assume. But there may be some other centroids also. So for that, generally, the centroids will get updated. How do you update the centroids is, you can take the values and find the average. For example, here if you can see here, what are the values that fall into first cluster? You just see here, 185, 179, 182, 188. So take all the 4 and just divide it by 4. I'm just showing you the different color. 185, 179, then next one is 182, then next one is 188. So 185 plus 179 plus 182 plus 188 divided by 4, you get the value as 183.5. Now similarly, you have to take for y. So what is the values with respect to y here? 72, this is 68, right? Then next is 72, then next is 77. So 72 plus 68 plus 72 plus 77 divided by 4. So you got a new cluster, 72.24. Now cluster 2 is centroid again. You can take it with respect to instances which fall into class 2. What are the instances? 170, 168 plus divided by 2. 56 plus 60 divided by 2. So new cluster centroids are 169, 164. Now what you can do is, this becomes your new centroids. What are your new centroids? 183.5, 72.25, 169, 164. This becomes your new centroids. Now with that, again what you can do is, you can go and calculate the equivalent distance for all the data, right? You might get a new set of class allocation. Now how will I stop that? Somebody would say, should I repeat it to the next and so on. See, the ideal way of doing is, that should be a balance. That means balance in the sense, number of instances that is got classified into class 1 and class 2 should be almost uniform. If I got 5 instances to class 1, 4 instances to class 2, at that point, you can complete saying that, okay, cluster updation is completed with respect to centroid, right? The other way of doing the same thing would be is, you can try reiterating the clusters until, right, you are able to find the clusters distances are minimal. That means the distance of cluster 1 with the cluster 2 is minimal. Are you getting? So if you see here, with respect to the distances, you have said the centroids are 185, 72, 170, 56. Maybe if you try keeping doing, the centroids may get reduced and you might find a closest clusters, right? So third is, whenever there is a possibility to combine more than one cluster into one cluster, it is better to do it. I just got 3 instances in one cluster, 2 instances in another cluster. In third cluster, I got 10 instances. If you feel the intra-cluster distance between cluster 1 and cluster 2 is minimal, you can combine the 2 clusters and make it as one cluster, right? So that's also an ideal choice. Right? So now the theory part of K-means is over, right? Now what we would see is with respect to the demonstration with the real-time data. At this point, any questions from the participants? Participants, any questions from your side? Am I audible? Participants, am I audible? Any questions? If you have any questions, you can put it in the chat box. I'm getting no questions. Okay. Fine. There's no questions. I believe that you are able to understand whatever I'm trying to teach to you here. Now let's move on to the next part. We would be interested to demonstrate the concepts. So we just first open the data. Give me a second, I'll share the screen. Just let me set the program environment, all that. I will demonstrate it using Google Colab so that it is uniform and understandable for you. Now, let's move on to the discussion part, right? So, any model generation process, as I told you, will start actually with data, right? So, without data, no model generation will succeed. Now, here, the data that we are going to take here is partially belongs to the intuition detection model. So, we will assume the features. So, as a constraint, as I told you, the features that you take can be numerical, as you can see here. Attribute 1, 2, 3 are all numerical. 4 is also numerical. Attribute 5 is categorical. Okay, attribute 5 is categorical. Attribute 6 is numerical, attribute 7 is categorical. 8 is numerical, 9 is numerical, 10 is numerical, and last attribute 11 is also numerical. So what is that we have learned today? We have understood that any categorical data will be converted to numerical data using one-not encoding, right? So attribute 5 will be converted to numerical, attribute 7 also will be converted to numerical, right? Now, whenever you want to implement such things in your Python, then you will have to use certain libraries for sure. So the libraries we will try to use in the code are, first will be NumPy, second is Pandas, right? Third is Matplotlib, fourth is ITERTools. Since we are going to work with an Excel sheet which is a CSV format, so we would say import CSV. Then math, we need some visualization. So for that, SCI-Kitplot, right? Then we will use a very interesting library called as sklearn. This sklearn as such is a machine learning library. Just see here. sklearn is a machine learning library, right? So when it comes to deep learning, it is Keras, TensorFlow, right? TML. That also we will see, right? ML, it is sklearn. So installing that, as I told you yesterday, in your Anaconda prompt, you can always install saying pip install. Let's take, I want to install sklearn. So you can say pip install sklearn. It will connect to the internet and it will download the library and it will install. You can see. Now I think people will know these are libraries that we are using for the code. Now the data set that we have taken here is a generated data set from our side, where if you see here whether there is any class label, there is no class label. So what is the theory here? We said yesterday, when there is no class label, you are supposed to use an unsupervised algorithm. So here we will use k-means, right? Now this is the only data that we have. So we want to do training and testing. So as I told you, you can split your training and testing data sets. So you need some data for training, you need some data for testing. So here the training data size can be specified in terms of numbers, or you can specify your training data size in terms of percentage. I will again repeat, the training data size can be in terms of numbers, or you can specify your training data size in terms of percentage also. Same thing is for testing also. You can give it in terms of numbers or you can give it in terms of percentage. So the ideal is like this. If you have n number of records, n indicates your number of records. If you have n number of records, so what you can do is you can take 70% for training, 30% for testing. Some papers in state of art will say 80% training, 20% testing. Sometimes industries, they will say we are using 75, 25, right? All this is a right set of values, but again, whenever you do your research or with respect to your project, you go to the research papers and see what they are doing. Are they using 70-30, 80-20 or 75-25, right? At this point, I wanted to know one more interesting data set which is there for all this cybersecurity problems, which is KDD dataset. KDD dataset, right? So you can actually use this dataset also, because this is also a very popular dataset for analyzing cybersecurity relevant attacks, right? Whenever you want to develop models to check for the vulnerability of the data, there you can go for this KDD dataset also. There's a lot of research papers with KDD dataset, right? If you go and type KDD dataset, IEEE, for example, you can see here, right? You'll find many papers using KDD dataset. It's a very standard dataset for network intrusion detection, right? So please have a look at this dataset. Okay. Now the next one which I want people to know is, other than this, IEEE also provides standard datasets for people to work, right? So that datasets you can see it under the IEEE data port. Any project research that you do, it can be image processing, synthetic data set, whatever you do, you can actually go and you can download some datasets. For example, you can go and search datasets, whichever dataset that you want. For example, you say, I want to look for datasets with respect to intrusion detection, right? You can search. You will try to come back and say what datasets are available related to intrusion detection. Right. So similarly, you can look for any data sets that you want. You can see here. MQTT, IoT, IDS 2020. Right? Like this, these are just data sets. You can actually go and download this. Only thing is, they will ask for a login in IEEE. Most of the colleges has that, so you can go and download the data sets. Right? Okay. This should be a useful information for all the people doing projects or research in this similar line. Now, let's come to the code part. Now we have talked more on data sets. Let's come to the code part. So here, for supervised model, we are using KNN. For unsupervised learning, we are using k-means. So here we say import k-means, import KNN, that is k nearest neighbor. Right? Then next, we would like to show some performance metrics. So first is confusion matrix. Then we want to see precision, recall, then the precision score, then the average precision score also we would like to see. Then in the code part, we would like to read the data set first. Then what I told you, we need to convert categorical data into numerical data. That means use label encoder, which will do one not encoding, right? So what does it do here? It will actually take every column, right? Wherever it is a categorical value, it will convert it to a numerical value. The next would be is like we need to fix the number of clusters. You can actually start with 2 clusters, 3 clusters, or 4 as your choice. Here we are fixing the number of clusters to be 3, right? Then we are calling the data. We want to insert a column called as class. Because if you see this data here, we do not have a column called as class, right? So you want to insert a column called as class. Then we want to call k nearest neighbor. Okay, because when we call k means what it will do? It will take data, it will try to provide the class name. Okay, and then we'll again try to predict the class name. Now the question is, what is the percentage of splitting? Here we are given it as 30%. That means training data is 70, testing data is 30. You have 100 records, 70 records for training and 30 records for testing, right? So once you've done it, then the next step is we want to predict. That means given the test data, that is 30% of records, we want to predict using k nearest neighbor. Then what we want is we want to print the total number of data. What is the 70% of the data? What is the 30% of the data? Then we want to print the confusion matrix. As you can see here, the next what we want to print is actually the precision recall curve. Fine. We want to print the precision recall curve and we want to print the accuracy score also. Okay. So that's it here. Now we will move on to the code part. Fine. We will move on to the code part here. Now let me take the environment. Now what I am going to show you is with respect to Google Colab. Just 1 second, it takes a minute to load. Meanwhile, if people have any questions, you can just post it in the chat box. I'm not getting any questions, so I'm believing that you do not have any questions. Okay, now let's move on to the next part. Next part is we would like to see the demo of how it works. So let us share the screen. Here. So now what we are going to see is the working of k-means and KNN. So we'll open a new code block, right? We'll open a new code block here, right? So we will take the code, we'll try pasting it because this is a Python file, but as you know, Google Colab accepts Python notebook file. So I'm copying first the libraries from here. I'm going to the environment and just pasting. Now let me run. So certain libraries we have run earlier, so it is showing error. So we will go to that. Open a new notebook file. Okay, fine. So this is the folder view of this, right? Of this new notebook file. This is a folder view. So let us go and paste the code. Let us run. So it is showing one error. Let's see this error. Yeah, no module named SCI kit plot. Right. So okay. Learn. I'm showing it in Google Colab because this is easy for you to work. Otherwise, this code works perfectly fine in Anaconda because there we will go to install all the libraries. Now first we have copied the libraries code. It is working. Now we'll add the code part, the next part of code. So next is we need to access the data set. So we'll go here, we'll copy the code, paste the data set. Now here it will say that it is not able to see some data set like this. So what you are supposed to do is go here, right? Now you can click on this, you can upload the data set, right? So we'll go here, we will upload the data set. Before that, we'll close the file because it should not reflect any changes. Okay, not reflect any changes. So So it says that it will get deleted once you come out of this. That's a warning message. Once you come out of this, it will get deleted. That's not a problem. So let's go and run this. So, no such file. Yeah. So why it is saying here is the code file that we are creating, right? You just move it here. Okay, to separate. Now you go and run this. It will accept. You can see here. Just run it. Okay. These errors are small errors. You have to patiently correct it. That's all. Now add a code block. Now go to the rest of the code. Now we want to copy this and run the canes. And cane. Copy this. Go to your environment. Run this. Paste it under. Now it is working correctly. So what it has done is it has taken the individual rows. For each of the rows, it is given the class label. Since the k-means cluster value, we are giving it as 3. Right? The value of clusters is 3. Right? It is trying to fix each row into any one of the 3 clusters. That means 0, 1, 2. Okay. Now we just add a code block. Now the code block is created. Now we'll go here. We will try to print the instances. Instances means we are interested in printing how many number of instances are there, what is the precision value, recall value, confusion matrix, all that. So we'll copy this, we'll go here, we'll paste it. Now, if you can see the output, this is the confusion matrix. The confusion matrix says that it is a plotting between class label, saying the class labels are properly classified. For example, if you take class label with respect to 0, 10 instances.
सिस्टम समझ में आ रहा है अब मेरा महीना का 1200 रुपये
Class table
तो
1.
फिर वो इस कॉलेज है वो भाई किस्मत है सिर्फ मतलब वो अगले वाले के मूड पे डिपेंड करता है अरे भाई साहब देखो जाते समय तुम्हारा अगर 30 रुपए का खर्चा लगे चाहे 20 रुपए का खर्चा लगे ठीक है जाने समय क्लियर आते समय क्या है यार? बिना लिए हाँ महीना दिन में वही ये सब दिनों का बहुत मत देना
I think somebody's audio is on actually. Yeah, now it should be okay. Fine. Now this is your confusion matrix. So wherever you get values other than the diagonal, it means the misclassification. Suppose here I get 5. That means 5 instances of class label 0 is misclassified as 1. If I get 3 here, it means 3 instances of class 1 is misclassified as 0. Right? So that's the meaning here. Now, confusion matrix is done. Now the next one that we plot here is a precision, recall, F1 score and support. So with respect to class 0, how much precision value? 100%. Class 1 it is 100%. But this is not the ideal case always. If you give some other data, no, you will get different class precision and recall. Now the next one is the precision curve. Class wise, what is the precision value? Right? Similarly, class wise, what is the recall value? So this is the output with respect to k-means and k-mean. So here we have taken for 7 records, 7 features. Like this, you can extend it for n number of features for the given data set. Right? But same code will work. Any questions from the participants at this point? Participants, any questions? If you have any questions, you can put it in the chat box. Or if you do not have questions, you can say no questions at least, because we are virtually talking, believing that everybody is listening. No questions. Okay, fine. Now what we have completed is about k-means with k-mean. Now yesterday I told you that there's a very other interesting classifier called as an AdaBoost classifier. The advantage of AdaBoost classifier is it actually works on the principle of saying it will have a weak learner. Multiple weak learners together will try to create a strong learner, right? Multiple weak learners together will create a strong learner. That's the concept of AdaBoost classifier. And AdaBoost classifier is used for most of the applications. Reason is it reduces the outliers. The most important thing is it reduces outliers in the problem. Whenever you have outliers, no, then the performance of the model also will get reduced. Please understand this always. When the outliers are more in the given data, then the performance of the model will get reduced a lot. Right? So now let's look at AdaBoost classifier and then we come to the code demonstration of AdaBoost classifier for inclusion data. Right? Now I'll show you the screen. When you come to AdaBoost classifier, the purpose of AdaBoost classifier is it will actually have lot of weak classifiers. Combining the weak classifiers, the AdaBoost classifier will be able to work. And it principally works on an approach called as boosting. Right? So when you say that you have learned something, when you are able to learn with multiple hypotheses, the learning component increases. So this is your algorithm with respect to AdaBoost classifier. You can see here. So the AdaBoost classifier will say, you give me data, assume the data has to be as x1, y1 to x1, yn, right? So you will train a weak classifier based on a distribution. We will call the distribution to be d suffix t. We will get first a weak hypothesis, we will call it as h suffix t, right? Once you get a weak hypothesis, then the next step is you will try to find out whether you have got a hypothesis with a low weighted error. So what is low weighted error? It equivalently indicates that the classification accuracy will be improved when the hypothesis is correctly fixed. then you will calculate alpha suffix d, right? And every time you will update the distribution as the distribution in consecutive order. Original distribution is d suffix t. The next distribution will be d suffix t plus 1. This will be keeping on going until it gets a final hypothesis, which is called as capital H of x. So this capital H of x would be given as summation of I equal to 1 to t, that is capital T here. This t is nothing but the iteration limit. The next is alpha here, that is alpha t. The next would be x suffix t of x. X suffix t is nothing but your hypothesis. So this is how Adabos classifier works, right? Now let's go in and see how our IDS dataset that we have taken works for an Adabos classifier. Why do we do it? That's a very important thing. So whenever you do your model, you cannot conclude that I did a model with K-means KNN for a security dataset classification. It is working correctly, so I'll stop here. It's not a good way of doing it. And with some classifiers. Ideally, you can compare with classifiers which behaviorally vary. For example, K-means worked on distance, but Adabos will work on kernel based. So you are trying to compare a distance based approach with a kernel based approach to see which classifier is better. That's the whole idea here, right? So let's do that here. So we'll go back to the code block. Now this is our code block here. Okay. Now let's take a new code book and see how Adabos will work. Okay. So go here, new notebook. Now we are going to see the working demonstration of Adabos classifier, right, for same data set. Okay, how does it work? So let's take the code. This is a code for Adabos classifier. The first set of code will resemble what you saw in K-means, right? Only thing is we need Adabos classifier. So we'll say sklearn.ensemble import Adabos classifier. sklearn.ensemble import Adabos classifier. So we just copy this, right? And we will come back to our code editor, paste here. Now you can go and run this. Meanwhile, you can open this folder view also for your reference. Right. Now, let this run. Now, we need to import data for this. So, we'll go here, upload data that we need for Adabos classifier. So we'll go to the Adabos folder. We'll take the data set. Right? Again, this is the same message. It says that once you go from this runtime in your kernel to other one, it automatically gets deleted. That's what it's saying. So nothing to worry. So we'll go here. So what do? We are supposed to take this data set and keep it outside for the code to access. Now we'll insert one more code part. Now we will go here. We'll try to take the data set that we have. So we'll go and we'll copy the code. Now in this, only difference that you can find here is the code will resemble to what you saw in K-means. Only difference is like we are interested in finding out the working with respect to Adabos classifier. So we will call the method which is Adabos classifier, right? So to that we need to pass some parameters, which is base estimator, number of estimators, learning rate. I think people know what is learning rate. We discussed yesterday. The next it will ask you what is the algorithm part. The next is random state, all this. this is an inbuilt method which is there in Python, right? So if you go to internet and type AdaBoost Python, AdaBoost classifier with Python, you will get the URL of AdaBoost classifier with Python. I'm talking about from the sklearn library, right? You go to the sklearn library, then you will find AdaBoost classifier. Are we okay? Right? Fine. So this URL is just for you to understand more inputs about the parameters of AdaBoost classifier. Now let's come to the code part. So we move on to the code part here. So this is your code environment. So here you go and run. So once you go and run, now the AdaBoost classifier works with the k-means classifier. Now we get the outputs. So first what we are getting is the k-means cluster centers. I'm printing this for you to understand that, because in theory we said there's something called as cluster centers. We are not shown cluster centers in the last code, but here you can see there are cluster centers, right? Okay, there are cluster centers. We're just printing the cluster centers for your reference. That's all. The next is the confusion matrix. We are looking at a 3 class here rather than a 2 class last time. So it's a 3 class here, right? So class wise, how much amount of instances are correctly classified? Class 1 classified as 12. Class 1 misclassified as class 3 is 3. Class 3 no misclassification. So you can try to do something in AdaBoost also by varying the type of kernel in such a way that this misclassification that you are seeing, no, as 3, which says class 1 misclassified as class 3 is 3, becomes 0, right? This becomes your performance metric. So precision is 80%, recall is 0.86, accuracy is 0.72. So this is a way in which you can compare classifiers to say that you are able to classify the type of attack given an anomaly data set or a data set that's got malware classification as an input. Any questions at this point from the participants before we move on to the next one? Can you put in the chat box? Any questions? There's no questions, you can say no questions at least. Participants, if you have any questions, please put your questions in the chat box. If there's no questions, you can put no questions. Okay. Am I audible? Hello? Madam, am I audible?
Yes, sir.
Okay, fine.
Yes, sir.
Now we want to one more. Come back to the. Right? We move on to one more architecture and then come back to.
Yes, sir.
Okay, fine. Next, 1 second. Come back to the. We move on to one more architecture and then come back to.
Yes, sir.
Okay, fine. Let's go to the next one. So next we will see an architecture for reference. So here we will look at an architecture which is most interesting and now it is used most of the time. The architecture falls into GRU, that is gated recurrent unit. This GRU is very interesting because it is also has the capability of remembering the data. That means you give data and you are trying to train, it will be able to remember the past data and compare it with the current data. That's the first advantage of GRU. And second, it gives you interesting concepts called as gates, right? GRU says that you can actually use concept of gates, with which you can say I'm remembering something, I'm forgetting something, or I'm remembering everything, I'm forgetting something, right? So what you want to remember can be controlled when you go to GRU architectures, right? So GRU stands for Gated Recurrent Unit. It is again a type of RNN architecture. So it has got two gates. First gate is called as update gate. Second is called as reset gate. So if you have a value 0 in the gate vector, it means that it is unimportant and it is discarded. If you have a value 1 in the gate vector, it means that the values that you have, that means the data that you have, is important and it will be used. This is your GRU architecture that you see on the right side. You have a hidden state and you have two gates. One is update gate and next is a reset gate. So you use two functions. One is signal and second you are trying to use here is a tanh, right? As you can see here, for any given input that is being provided, there is a hidden state that works together and you can participate either in an update or reset. Okay, update or reset. Why are we discussing this GRU architecture is, since the data that you take varies temporarily over time. For example, if you talk about architecture of GRU and you look at the IDS problem, if you say how much records are getting created, somebody would say my network is switched on for 1 minute. If you ask how many records, you would say maybe 1 minute I got 1 record. But if I ask you like how many seconds are there, there's 60 seconds. So if I ask you how many records would have got created, assuming every second there is a ping packet at least going to the rest of the network, then you would say there are 60 records. Now if I go inside more and ask you, every second is basically can be represented as milliseconds. How many records you would have created, right? There you would say 7 records. Now my network is for 5 is on, so 5 into 60 seconds. Again, you convert into milliseconds, larger size of records. There, you need architectures which can efficiently manage. GRU is one of it, and in line of it, you will have LSTM also. So, how does your GRU work? Let's see that, right? So, this is the equation that is there for resetting, right, for the gate, which says that you can apply sigmoid function, right, of W input reset into X plus W head and reset into X suffix T minus 1. Now the same thing if you take with respect to the next variable that you will be calculating every time, which is called as R, which indicates a reset. This will be given as tanh of gate reset multiplied by WH1 into H suffix T minus 1 plus W suffix X1 into X suffix T, right? You can see here the value of R which I am talking to you is this one, right? So how does an update gate work? So an update gate works by first calculating the gate update value, which will be given as sigmoid of W input update into X suffix T plus W hidden update into H suffix T minus 1. You will get gate update. Now that you take and multiply with H suffix T minus 1, you will get the next one which is called as U. So R is one which you get with respect to reset. U is one which you get with respect to update, right? Now is about the final output. So final output is you got U and you got R. So the final output would be expressed as H suffix T is equal to R into 1 minus gate update plus U, right? So what are new hidden state that we got with respect to the output? Because what you get here is a new hidden state. That is H suffix T, right? Will be used for the next input analysis. This is about GRU, right? So the next architecture we will take in is LSTM, long short-term memory architecture. Now, till now we have seen 3 architectures: CNN, which is convolutional neural network; The next one we saw is RNN, which is recurrent neural network. Third architecture that we have seen is LSTM. Third architecture we have seen is GRU, which is gated recurrent unit. For the fourth one, we are stepping into is LSTM, long short-term memory. So as the name indicates here, no? If you have a longer sequence of data, but you want to have a better representation for processing, there you can go for LSTM. Why should you go for LSTM? That's the first question somebody would ask. Before that, let's say, what is the disadvantage of going for RNN? In RNN, whenever you want to add a new information, you have to completely modify by applying a function, right? That means, if you say you have a sentence S1, if you say a sentence S2, please listen all of you. If you say you have a sentence S1, you have a sentence called as S2. If S2 is totally different from S1, right, there RNN is best. Please make a note. S1 is one sentence that you speak. S2 is another sentence that you speak. S2 is totally different from S1. There RNN is good. But let's take the sentence S2 that you are speaking is partially related to S1. That means you can try to relate S2 with S1 and say there is some sort of associativity between S2 and S1. Right? There the concept is you cannot go for RNN because RNN will allow you to modify the entire information and consider it as a new information. But LSTM is not like that. LSTM will say, no, I can modify partial information or I can remember that, right? So LSTM will say that I will represent everything as a cell and cell will have states, right? I will represent everything as a cell and cell will be having states, right? So let's take through this with an example. So with respect to LSTM, we have got gates. So the gates will have names. So for example, here you have forget gate, right? You have forget gate here. So the purpose of forget gate is to remove some information from the cell state. So whenever you don't want to have any information, then you can remove that information as part of LSTM by just invoking the forget gate. The gate will have two inputs. First input will be h underscore t minus 1 and second input will be x suffix t, as you can see here, x suffix t. X suffix t minus 1 is a hidden state from the previous cell. X suffix t is the input at the particular time. Once this is provided, what happens is the inputs will be multiplied by the individual weight matrix and it will be added with bias, because we already told you it is wx plus b. We already told you that it is wx plus b. So it will be multiplied with the individual weight matrix and it will be added with b. Then the input goes to the next part where we apply a sigmoid function. The sigmoid function will output a vector where the values of the vector will range from 0 to 1. Right? So this sigmoid function is responsible for deciding which values you can take and which values you can remember. Right? That means which values you will consider. That means certain values will be discarded. So if you have a 0 as an output for a particular value in the cell state, then that means that the forget gate wants to forget that information totally. If you have a 1, right, then that case the forget gate wants to remember the entire piece of information. So this is a concept. So you can either forget completely or you can forget partially from the original information using LSTM. The next gate is called as input gate. The purpose of input gate is wherever you want to add some new information, you can add it using your input gate. So the input gate will be helping you to add some information all the time, right? Okay. So let's see how it works. So it's got 3 steps. The first step is you check what are the values you will add it to the cell state, right? and it will take two inputs, as you can see here, x suffix t minus 1 and x suffix t, right? It will create a vector with all possible values which will be ranging from -1 to +1. Now, when you multiply the value, right, with the useful information that you have, then you will be able to get a resultant value here, right? This is about input gate. Now, let's go to the output gate. What an output gate will do is, it will try to select useful information and it will show it on the output, which is on the output gate. So what will be the steps? It will first create a vector after applying tanh function to the cell state, and it will have the values to range from -1 to +1. It will have the values ranging from -1 to +1, right? Then second step what will do is, it will have a filter which will use the values of x suffix t minus 1 and x suffix t, okay, and it will try to regulate the output by using a sigmoid function. Then the third step is, it will multiply the value of the regulatory filter along with the vector which we have created in step 1, right? Step 1 is what you see here, where we are creating a vector, and it will send it to the output and also to the hidden state of the next cell. Okay, so this is how LSTM works. Now, somebody would have a basic question. We have seen so many architectures. Can you quickly say which architecture is better? Where should I use for what type of architectures? See, the state of arts research says that whenever you want to try any deep learning model, you can compulsorily use CNN, because without CNN, there is no deep learning. But if there are variant architectures available on a same one, for example, there is somebody who has done GRU already, you would like to go and see how the GRU can be modified, there you can go and modify the GRU architecture. So next question will be the comparison of all these architectures. So let's see the comparisons here. So the first one is with respect to CNN and RNN. CNN is very powerful compared to RNN, but only thing is CNN do not have capability of remembering, right? And RNN has the advantage of remembering the data. And as we told you, wherever there is a longer sequence of data, there RNN is better compared to CNN, right? And CNN is generally developed for image processing, video processing initially. Now people are using for CNN for synthetic data set. That means a data set in an Excel sheet where you are representing the data as a 3x3 matrix as similar to an image, right? The next, with respect to your GRU and LSTM. GRU has less training parameters, but LSTM has got more parameters compared to GRU. GRU takes less memory, LSTM takes more memory. GRU executes faster and trains faster. LSTM executes slower and trains slower. GRU has less accuracy on a longer sequence. LSTM has got more accuracy. Then GRU will require less memory. LSTM will require longer memory, but the advantage is it can give you a quick sequence learning, even if the sequence is very long, especially with respect to IDS and all. We have features where there are 100 plus or 200 plus features. There, LSTM is very efficient compared to GRU. Any clarifications to the participants till now? Okay. So if there is no clarifications, now we will take one code sample related to deep learning. So there are many papers which are there with respect to deep learning. So here we will look at a code sample which is there with respect to KDD data set, right? So that in future also you can actually use the same for your research. Once again, I'm sharing the screen. Yeah. Now I share the screen. This will get you the source for you to further work when you want to do projects or research. This is one URL that generally works for anomaly detection. So if you come down to this URL part, now I share the screen. This will, yeah, I'm sharing the screen. I'll share the screen. Source for you to further work when you want to do projects or research.
In contact.
This is one URL that generally works for anomaly detection. So if you come down to this
ఇప్పుడు 10 నిమిషాలు అయిందా?
part,
10 నిమిషాలు అంటే తెలుసా అతను మీకు?
I think somebody sounded. Okay, I think it's fine here. So this is the URL which I want you to have a look. So here they have used KDD Cup 99, then they have used NSL-KDD dataset. They have used one more dataset called as UNSW NB15 dataset, right? So all these three datasets have been analyzed by them, and they have tried to use the code for anomaly detection. So you can check through these codes. So codes are there for anomaly detection, and all these codes are built on Python. So you can use the codes for working, right? So this is a URL I would like to share to the people for working for basic cybersecurity problem, which is there on the internet. Now, the interesting thing is people will generally ask if I'm going to use deep learning as such, right? And I'm going to use it in my real-time problems. There are users, there are hackers, right? How do I understand this, right? So let's see this. There's a very popular architecture which is there proposed, which is called as CryptoNet, right? Which actually talks about how to secure the data, especially for models where the data needs to be very large. The data can be anything, an image, or the data can be a normal data also, right? Now this is also taken up from Microsoft also. So they also have a model library for CryptoNet. As you can see here, this is the URL for downloading the libraries with respect to CryptoNet, right? This uses the concept of homomorphic encryption. I think the other expert will talk to you on homomorphic encryption. If you see here, you can see the codes for this, right? Now, I want you to see one more implementation, which you can see. This is with this architecture, which is called as GAN. See, this is a very promising architecture in deep learning because this architecture says wherever there is a randomness in the type of data, for example, you have created a model, you feel that model is working correctly. Suddenly, somebody says, I gave an input data. For that data, the model is not working properly. It means that your data that with which you have trained is limited. So what is the answer? You would say that I will go and use that data one other person has told. With that also I will check whether model works. I will improve my model. But that becomes a never-ending story, right? Let's take another 10 people comes with new data and ask you to fit to the same model. You again fit with that. It keeps on going. That is where deep learning people, they developed a very interesting architecture which is called as GAN, right? Which stands for Generative Adversarial Networks. It's a very promising research area for projects also, right? So the advantage of GAN architecture is the GAN architecture will say there will be something called as a generator, there will be something called as an addresser, right? There will be something called as a generator, there's something called as an addresser. So rather than going and modifying the model based on the input data every time, what you can do is you can actually try developing a generator, and that generator as such will have the capability of modifying the data. So the generator will take data, right, and it will try to create all possible data for it by fitting to a distribution. For example, in a class, if you say the minimum mark is 50, maximum mark is 100, if there are 50 students, you will give randomly 50, 60, 70 till 100. But you can try all possible distributions to generate that 50 to 100, right? So that's a concept. So GAN says that I use a generator model to generate data, right? So whenever I'm calling the discriminator should be able to classify and say whether it is a real data or it is a fake data, right? If it says correctly whether it's a real or fake, what is real or fake? It's a two-class problem. Please understand. It's a real or fake means it's a two-class problem. If my discriminator is correctly able to go and say it is class 0 or class 1, then my generator is lost. So my generator should become again intelligent. So my generator again has to improve on the data creation process with a new distribution and generate the data. Now again what will happen? The discriminator will again go and check and classify it as 0 or 1. If it classifies correctly as 0 and 1, again what happens? Then my generator is lost. It's a win-win game between generator and discriminator, right? So people develop this architecture. There's got a lot of attention now. There's a lot of people who are actually working on GAN architecture. So now what I would like you to see how the GAN architecture actually works, right? This is a code URL, which is a working URL code. So what I'll do is I'll go to the chat box. I'll put it so that whenever you have time, please run this code and check. It will give you good insight about how crypto models work with deep learning. Okay, I put it in the chat box for your reference. Right? Now, what is this architecture implementation is? If you go and see here, you will have individual Python files, right? For data loading, for GAN, you will have individual Python files. Now, as you come down, this is your visual demonstration. This says that you have a plain image, you have a key with which you want to encrypt the data, right? So the image is encrypted with a key, which is again an image. So you get Latin vectors, one for the plain image, another for the key image. Now what you do is, it is getting transmitted over the network. Now here what happens is, there is a hacker. The hacker is called as Eve. The hacker as such tries to hack the state. If you go for conventional algorithm, somebody says, I'm using RSA, this person is able to get my key with which I have encrypted, then this person Eve can actually decrypt my data. That's the usual concept. But here, I don't want that to happen. So here in the middle, I'm doing my GAN architecture. So what does my GAN architecture says? It says that I will try to first do the generator part working, right? So the visual demonstration is shown for your reference. Just see here, as the data is combined, right, then automatically the GAN architecture will work in the middle. It will try to generate the weight matrix model using GAN. Whenever the hacker is trying to hack the data, that means the Eve is trying to hack the data, automatically the hacker will not be able to hack because the hacker will not use a similar set of architecture parameters which is being set for the GAN, right? So that is the strength of this model, which is the CryptoNet model. So this is a working code procedure. You'll have a file for autoencoder, you'll have a file for training process, right, which is feed forward neural network, and you'll have a code execution file for adversarial training, right? So this is the next one that I want people to know. So now we have come to the end of things. So our discussion today has been around talking to you about what is deep learning advantage as a quick summary related to yesterday's session. Then I have discussed to you about the other architectures which are related to remembering, partial remembering, which is RNN, LSTM, then GRU. We have seen working implementation of K-means, KNN, AdaBoost with K-means on a network security data set. We have seen the performance parameters also visually working. Then the next step that we went into is understanding about the code which is there on the internet. So there I have shown you architecture here, which is CryptoNet, which is completely built on GAN, Generative Adversarial Network. Any questions at this point? Participants, any questions at this point? There's no questions. Thank you so much for your patient listening. Thanks to the organizer, thanks to Dhanlakshmi ma'am. I left my email ID in the chat box. Madam, am I audible? I have completed my.
Sir, okay, sir.
Participants, any questions at this point? There's no questions. Thank you so much. Yeah, thank you. Thank you. I left my email ID in the chat box.
పంపించిన అది ఇది not పెట్టు.
Yes, sir.
Thank you for the session.
Yes, sir. Thank you for the session.
So thank you all. Thank you for all your patient listening. Best wishes forward and stay safe. Thank you, ma'am. I leave
I
here.
request all the participants to please wait for 2 minutes. Yes, sir. Thank you for the session.
Thank you, ma'am. Thank you all. Thank you for all the patient listening.
Thank you, sir.
Thank you, ma'am. I leave here.
Okay, sir. Sir.
Okay, thank you, ma'am. I leave here. Thank you.
తొందరగా పంపి అన్న